For me to introduce our speaker today from Poland, from the University of Wroclaw, Krzysztof. I was training a lot, but it's difficult. Debicki, and today he is going to speak about, as far as I know, about the extremal behavior of integrals of Gaussian processes and some related topics. So let's start.
Thank you very much. At the very beginning, I would like to thank the organizers for inviting me to this wonderful place. So Sergey is not present yet, but Sergey, thank you very much. Everything is recorded, so.
He's running downstairs.
Okay.
No hope. And let's give him applause.
Okay, so let me start from the description of the problem. So I will start from the theoretical problem, and then I will go to some examples where this problem is appearing. So let Z be a stationary centered Gaussian process. With a covariance function that satisfies the following assumptions. So we will have three assumptions. So R of t is the covariance function of our stationary Gaussian process, which probably I should define. And we assume that our covariance function is continuous. It's non-negative and decreasing as a function of t. The second assumption is a bit more interesting. So we want to know what is the local behavior of the covariance function close to 0. So we assume that when t goes to 0, our covariance function has the following asymptotics. So this is when t goes to 0, and lambda has to be positive, alpha has to be in the range between 0 and 2. Later on, we will forget about this lambda, because we can always rescale our process just to have a lambda equal to 1. And the third assumption is related with the behavior on the large scale time of our covariance function. So we just want to be sure that our covariance function goes to 0 sufficiently fast for some beta and t larger than some boundary point t0. Okay, so what is the problem in which we are interested in? So we integrate our process, and then we look at the integral mean. So we divide by the length of this integral. And finally, we want to check if the supremum over positive half line is larger than u. So in fact, we are interested in the asymptotics as u goes to infinity. So that's the problem in which we are interested in. And maybe before solving what is the exact asymptotics of this probability, let me mention two examples or two motivations that stand behind this type of problems. So the first one is related with Gaussian fluid models. So a few years ago, together with Michel Mandiès, we were interested in the following model. So we have a single server Q with infinite buffer, and we assume that this Q is fed by large number of IID sources, and intensity of inflow of source number I is given just by process Zi. We assume that Zi satisfies these assumptions. So we have
Zi is intensity function.
Sorry?
Zi is intensity function of what?
Yes, this is the intensity of income to the buffer. So we assume that Zi of t are IID and satisfy A1, A3.
I'm sorry, so Z is Gaussian.
Z is Gaussian,
It
yes.
may take a negative value.
Okay, yes, but this is the limiting process. So if you think about large number of on-off sources,
No, but you say intensity may be negative.
yes, this may be negative, yes, but there is nothing about that, because this is the limiting process in the sense of central limit theorem for let's say on-off processes. So if you consider large number of on-off processes, then under special scaling, they converge to this type of processes.
So customer rate goes down.
Well, you don't see, no. You don't have this interpretation. You don't have this interpretation. This is like, central limit theorem for tossing coin. You can think about...
What does it mean in terms of single server queue?
Okay, so you can think about the limiting Q, and then when you take the limit, then in the limit you will have the representation where you can see this process Z in the place where you had this intensity for your original processes. So in this sense, this is intensity, but of course there is no physical meaning of this, because this can be negative.
You have to center to normalize.
Yes, I have to center, like in central limit theorem, exactly, yes. So, okay, so maybe I will make a short digression. So if you have large number of on-off sources, yes, n, then what you can do, you can just sum them, let them be eta, intensity, yes. You integrate, and if you consider this type of functional, then this is the buffer content for this model. And then you can ask, okay, what will happen if I divide by square root of n here and go with n to infinity? So it is possible to prove that this converges to this process. where the correlation of this process, well, this is a Gaussian process, centered, stationary, and the correlation of this process is exactly the same as the correlation of one single on-off source. So in this sense, you can think that, okay, this is the intensity, but of course you lose this physical interpretation. Yeah. So you can think that you have capital N, this type of models, they converge, and you are after this limiting procedure. And then we have to say something about the output rate. So we assume that we are under many sources regime, which means that the output is rescaled linearly with number of sources. So if you are interested in the stationary buffer content, Qn, then the representation for this buffer content is the following. So are my fonts sufficiently large? Or okay. Minus C and T. Okay, so as I said a few years ago, we were interested in this type of models, and exactly we were interested in asymptotics of Qn when n goes to infinity. And what was possible to do was the asymptotics of the following probability. So B is larger than 0. And when n goes to infinity, we were able to prove that the asymptotics looks like a constant, which is known, times the tail distribution of standard normal random variable at a specific point. So we have here square root of n times some known constant which depends on C. Maybe I won't write this constant because this is not necessary here. And when we considered this problem, it was obvious to us that unfortunately we cannot extend this result to the case when B equals to 0. So our approach, which was based on a double sum method, so the double sum method is a tool which allows you to obtain exact asymptotics for, well, a large class of Gaussian processes. But this tool broke when B equaled to 0. And let us look what is going on when B equals to 0.
I didn't understand this formula. When n tends to infinity, you on the right you have constant times function of root of n. So it tends to 0, yeah?
Yes.
On the right.
Yes.
Of this order.
Yes, of this order.
It's not, it should be equivalence, not.
Oh,
no, right,
yeah. So maybe I should write like that formally.
Okay.
Yes. As n goes to infinity. Thanks. Okay. So let us play a little bit in the case when B equals to 0. So I will interchange summation with integration. So using that Zi are Gaussian, then the sum of Zi is again Gaussian. So this is equal exactly square root of n times 1 generic process z, which is distributed exactly the same as z1, z2, zi. Yeah, so here I did almost nothing. I just used the fact that sum of Gaussian processes is again a Gaussian process, and I can exactly describe what kind of process is that. Okay, so let us rewrite it a little bit. So I can divide by square root of n, and then I can write it in the language of there exists. So there exists t such that we have this inequality. So let me put this t here. And you see that this is exactly the problem in which I'm interested in. So if I abbreviate it by, let's say, p of u, then this is exactly p at point c squared of n. Okay, so that's the first motivation to consider this type of problems. And the second motivation is related to the problem of collisions of Gaussian processes. So there is a collection of papers by Bramson and Shaoli where kind of following problems is analyzed. Where is the eraser? Ah.
Go there, then
Not here. Ah, yes. Main erasers. Okay. Okay, so the second motivation. Let us consider two independent Gaussian processes with stationary increments and differentiable sample paths. And let us assume that these processes both start from 0. They evolve somehow. And I'm asking about the probability that they will meet again. Okay, so formally I consider two processes. Eta 1, since this is a differentiable process, then it can be defined in the following way. And eta 2 is as follows. Assume that C1 is larger than C2, and then the probability that the collision appears depends, of course, on slopes of these drift functions. And under the assumption that C1 is larger than C2, you can easily see that this is the same that eta 2 at some positive time will be not smaller than eta 1. Okay. So let us play a little bit with eta 1, eta 2. So we see that this is the same as Z2s minus Z1s ds. And here we have C1 minus C2 times t. So once again, I move this t here. And you see that in fact we arrived once again to our problem. Okay. So maybe before I will write it down, if you assume that Z1 and Z2 are identically distributed and independent, then this is the same as square root of 2 times just one process. Which leads us to the following. So we see that if the slopes diverge, then we are in the same type of questions as our original problem. Okay, so I believe it's time to go back to our problem and look how can we solve it. So maybe at the beginning, let me say something about the idea how to deal with this type of problems. So the rough idea is that in the first step, we have to look at the variance function. Variance function is the most important, that brings the information where the mass of the probability is concentrated. Okay, so we are looking at this process. So let it be x of t. Oh, okay. And first of all, let us look that if t goes to 0, then this process goes to z at point 0. So at point 0, let us define that this is just equal to z0. And then let us look at the variance function of this process. So this is nothing difficult. We can calculate it. And it's easy to see that the variance function is decreasing with t. So the maximum is attained at 0. This is very important, because in the case which was considered by me and Michel, this maximum was attained somewhere in the middle, not at the very boundary, at the very bond of the interval in which we are interested in. So the maximum is attained at 0, and variance equals just to 1 due to our assumption. So if we know that the variance maximizes at point 0, then we should look at the very neighborhood of the 0, and then the next step is to try to understand what is going on in the neighborhood of 0. So the classical double sum method works properly when local behavior of the process close to the point that maximizes variance behaves, roughly speaking, like a fractional Brownian motion. If this is the case, then the classical tools are available and exact asymptotics is doable. Unfortunately, it appears that our process behaves completely differently. So it appears that if we look at our process close to zero, namely if we look at the following then it doesn't converge to fractional Brownian motion as it is in this classical theory, but it converges to a kind of very interesting process. What kind of process is that? So alpha is this alpha from A2. So this process is related to fractional Brownian motion in many ways, and in fact it is even possible to define it via fractional Brownian motion. This is just the integral mean of fractional Brownian motion with Hurst parameter alpha half of alpha. So this is fractional Brownian motion with Hurst parameter half of alpha. So this process has many interesting properties. First of all, it is the example of self-similar processes. This process is self-similar with index alpha, so alpha half of alpha, exactly like fractional Brownian motion. Its variance is equal to variance of fractional Brownian motion, but its sample paths are differentiable. So we see that this is a kind of differentiable analog of fractional Brownian motion. Okay, so what is the advantage that we know what is the local structure of the behavior of our process close to point zero? Well, we can try to extend the classical Pickens approach, which deals with very tiny intervals. And let us look what comes out of this extension. Oh, maybe not this thing. Okay, so we can prove that supremum on a very tiny interval asymptotically behaves like that. So there is a constant which I define in a minute. This constant depends on this capital T and on this process, and then we have the probability that at point zero we are above mu. So just the tail of standard normal random variable. Yes, we can write this just in this way. but I believe that this representation brings more insight. Okay, so you see that looking at the supremum is comparable to looking at that at the very beginning you hit this level u times some correction which depends on the length. What is important that when u goes to infinity, this interval goes to 0. And alpha is the same as in A2. Okay, so what is this constant? So this constant looks similarly to the well-known collection of constants which are called Pickens constants, but it's a bit different. So here capital T appears, and we need to take square root of 2 times our process minus this type of drift. And of course, when you look at this, then you can even be frightened if this is finite. Well, this is. It's not difficult to prove that this is finite. The most difficult is to find exact value of this type of constants, and it's known only for a very specific cases, like here having just plain Brownian motion or this degenerated fractional Brownian motion. And for this process, well, it's even much more difficult. But at the very end, I will show you some bounds for these constants. Okay, so let us go back to our original problem. So we see that close to 0, we know how to deal with these asymptotics. So the rest and the last step is just to prove that we can really focus on this very tiny interval and to neglect the rest of points. And indeed, this is the case.
What does this coefficient represent? You said that one of possibility is to have at the very beginning something like that, but coefficient doesn't tend to. So it's a constant.
It's a constant, yes. So this is a kind of correction.
Which is strictly bigger than 1.
Bigger than 1, yes. Strictly bigger.
What means if we subtract the difference, this constant minus 1? What does it mean?
Okay.
Is there a chance to have above?
This is, yeah, in a different points. Yeah,
Why?
roughly speaking,
Why?
yes.
What is the path which leads to this? The first option is you are above level U at the very beginning.
Yes.
What are the other possible trajectories?
So you can be below at the very beginning, yes, and then try to go up in this very tiny interval.
Yeah, I understand.
So this is this.
How?
How?
So it's coefficient says something.
So you see that because this is a constant, then this is rather very unlikely. And if t is small, then this constant is really close to 1. So you see that the probability that you will be above u at the very beginning is, well, kind of dominating, but, well, not in 100% dominates. There is this correction which allows you to be also in this very tiny interval in different times to be above, but below at the very beginning. Well, there is, I don't think that there is any physical interpretation that stands behind this constant. So classical Pickens constants are related with constants that appear in convex geometry of Gaussian bodies. But okay, but this is, I believe, a completely different topic. So now let us look what is the last step. So we want to calculate the asymptotics of this type of probability. So of course for each t, for free we have this. So the only thing which has to do is just to be able to deal with the upper bound. So to do this, we need 2 steps. First one is kind of easy. So we choose small delta, and of course for each delta we have this inequality. And then because variance function goes to 0, the variance function of this process, it's kind of easy to prove that this probability is really negligible with respect to this one. It's much smaller. So there are many ways how to deal with that, but maybe the easiest one is just to use Borel type of inequalities. So this is a classical theorem in Gaussian, in extreme value of Gaussian processes that allows you to say something about the asymptotics. It's not very sharp, but it's very general. So it works for almost each Gaussian process you can imagine. And then we have to deal with that one. And this is a little bit more tricky. So we, the idea is that, again, if this is our interval from 0 to delta, then we look at this very first one of the length t divided by u2 power 2 alpha, 2 by alpha, and then the rest of this interval we divide by on intervals of the same length. And it appears that for each of this interval we can apply Slepian type inequality, which allows us to go from our original process to a stationary Gaussian process. And for stationary Gaussian processes, we have a well-developed theory, and we know what is the asymptotics of them. And then if we sum up all these suprimas, then once again, when capital T goes to infinity, it appears that what is going here doesn't matter. So finally, the asymptotics of our original problem looks as follows.
How do you choose capital T?
Okay, I go with capital T to infinity. That's the idea. So together with u, I choose t which depends on u. And when u goes to infinity, then t also goes to infinity.
Well, in essence, there should be infinity there instead of t, yeah?
No. Okay, then we go to infinity. Then we go to infinity. Here I can't put infinity, but yeah, then we go to infinity, in fact.
That estimate is that uniformity?
Yes.
Oh.
Yes. There is no problem because this goes to, this is an increasing function with t, so, and bounded, so there is no problem with uniformity. Yeah. So I can choose just large t, and I know that if this is bounded, when t goes to infinity, then I know that nothing wrong can happen. Okay, So the theorem is that, so let me go back to our original notation. Alpha. Where this constant is just the limit when t goes to infinity. And once again, you can wonder, well, if this is really something which is bounded when t goes to infinity. Well, yes, and this is due to the fact that here we subtract something a little bit larger than the variance function of this process. So let me recall that the variance function of this process is exactly equal to t to power alpha. And due to the fact that we have here 2, alpha plus 2 divided by alpha plus 1, this drift function is so large that in fact you can put here infinity and everything is okay. Okay, so that's the main result. So let us go back to our motivations and let us look how our two applications can use this theorem. So for Gaussian fluid model, you remember we were interested in the probability that our buffer is not empty. So this equals asymptotically to the following, and the collision problem has the following solution. And this is as C1 minus C2 goes to infinity. So the slopes diverge. So finally, let me say something about this strange constants. So as I said, they are very, very related to classical Pickens constants that for the first time appeared, well, 40 years ago in a pioneering work by Pickens, who considered just a stationary centered Gaussian process and the asymptotics of the supremum of this process. And then it appeared that these strange constants, which are defined in the following way. So the analog of this constant is just like that. So instead of this process, we have just fractional Brownian motion. And here you can have some constant larger than 1, sometimes equal to 1. So there were many attempts to calculate this original Pickens constants, and apart from these very specific cases of Brownian motion, standard Brownian motion, or degenerated fractional Brownian motion, so alpha equal to 2, well, there are only bounds available. And I believe it is very unlikely to be able, in the nearest future, to be able to say what is the exact value of these constants. So if you look at this constant, then it appears even more sophisticated. to be more sophisticated, since we have here kind of integral mean of this original fractional Brownian motion. But it appears that when alpha is larger than 1, we can find a very nice bound. So the bound looks like that. But it is true only for alpha between 1 and 2. So we see that, yeah, all the time it's bounded by 1 plus alpha. So it's not so large. It's kind of close to 1. Okay, thank you very much for your attention.
So you mentioned the original motivation is that you had a theorem for b bigger than 0, but you didn't know what happens for b equal to 0.
Yes.
So now you know the result for b equal to 0, and you compare it with the result for b bigger than 0. Is there a discontinuity?
Yes, yes, indeed. There is a discontinuity because for...
Is there only in the constant or?
Only in the constant, yes. So this is very tiny, indeed. So for b greater than 0, we used this classical double sum method, and as a result, we observed classical Pickens constants in the front of this main parts of the asymptotics. And here you see that really something very strange happens when you want to consider this very boundary case. So I believe that this really explains why we couldn't solve it earlier.
How do you know that these constants aren't equal? Like you say, I have one result in terms of one complicated constant, and another result in terms of another complicated constant.
That would be very strange, because you know, if you look at this process, then this is a differentiable process, this is not differentiable. So if you want to have equality of these two functionals, I don't believe it. I can't prove it, but I don't believe it.
But the original two probabilities, they are related, like one is bigger than the other, so you also get a bound
Yes.
for one constant in terms of
Yes.
the other.
Yes. Mm-hmm.
So, any other questions?